then she finished her PhD at the Villafranca at ISAC. Back then it was VISPA, I suspect. And then she moved to the European Coordinating Facility of a Space Telescope, and as a postdoc already. Then she went to work with Rosat, also at Garching, where the ECF was located. Then ESO, working with some very early VLT data. Then Heidelberg, and finally to the IAC, where she's now a researcher at the Instituto Astrofísica de Canarias. So I think we'll have some questions at the end of the talk by Almudena. So Almudena, if you don't mind, would you mind sharing your screen now so everybody can follow your talk? And by the way, thank you very much, Almudena, for willing to participate in our seminars.
Well, it's a pleasure for me.
Okay, so please go ahead. You have the presenter's view right now in our screen, so maybe you have to.
How is the point is that if I stop sharing,
I think you have to escape from presentation mode and stop sharing, then start sharing, and then go to presentation mode. That's what I think will work. Okay, now escape your full screen presentation in PowerPoint, and try to put it again in presentation mode.
Okay.
Like you did in the.
Like that?
Well, first you have to escape your presentation mode, share your screen.
Okay, because I had to go to your Zoom thing.
Yeah. In the wrong screen, that's possible too.
Zoom, share screen.
Yeah.
Then I go here, share.
Yeah.
And I go to.
Yeah, now presentation, and hopefully that will choose the right output screen.
And I can go presentation view.
Yeah, perfect. Great.
Okay. I don't see, but I will come. Yeah.
See us, but we can see you.
I see you again here, but okay, I don't mind to see you. The important thing is that I'm not sure if the screens, your faces are appear in my presentation. And
yeah, but it's not covered in your presentation. We can see the whole PowerPoint.
Okay, good. Okay, so yeah, thank you very much for having me with you, and thanks for being there. I just wanted to take this opportunity to introduce this project I'm working for as long now, a number of years. I'm not going to say the number, but quite a number. It's called parsec. I started in Heidelberg when I was there, and wanted to give you a bit an introduction, very short, and then focus on one of the aspects we study in parsec. But just to let you know what is about this project is a multi-wavelength investigation of the nearby galaxies, relatively nearby. We are trying to move a bit farther, but nearby you will see why. At parsec-scale, only studying the central part, the central region, the central kiloparsec at parsec-scale. So we try to cover a wide range of galaxies. Actually, we don't have a particular prediction for one type or another. Basically, everything that we can do at these high angular resolutions, and I'm talking about our limit is less than half a second, which nearby objects are a few tens of parsec, the physical scale, resolution scale. And we had to be limited to objects that are relatively bright because we use interferometry, we use adaptive optics. So that is our limitation. But otherwise, something that is close, so it could be very active. Of course, these are very good candidates to study in this project, or could be very quiescent. We go for it. And the thing is that we try to look at the nuclear region, central kiloparsecs in general, and we can compare galaxies with different activity or different category you want, but it's always the same or very comparable physical scales, which allow us to do a quite comparative analysis and comparative of the physics in different nuclei. We try also to cover the complete wavelength range from centimeters to high energies. High energies we cannot get to high these angular solutions, but okay, they are in because high energies are always very compact information. They come from high energies is usually from very compacted region, presumably the nucleus as well. And we try to keep comparable angular scale across the complete spectral range. So we are not comparing 1 second in one range and 0.1, 0.5 in another. So similar angular scale across the spectrum. And whenever is possible, very hard, but we try. Also time compatible, which is, as you can imagine, is quite difficult, but sometimes it's possible. So if the data is available, we try to be compatible in time as well, consistent in time as well. So there are two main, and by the way, here in the view graph, you see that 0.5 seconds is our limit in angular resolution, but for certain range of the spectrum where we can do space, or we can do adaptive optics in the infrared, or even the radio interferometry, we go to 10th of a second. Is possible? Although here I did not include the ALMA, I don't know. Okay, so there are two main projects or two main lines of research. They are connected, but one is studying the nuclear star formation or circumnuclear star formation that we can do in great detail at these scales, at parsec scales, and the other is what I will focus today is more the nucleus region, the entourage of the black hole, what is happening then, the ISM there. So I love the star formation as well. It's not possible to do everything, so I'm going to tell you about the nucleus of these nearby galaxies. Some are, you might see, are a bit more active, very active, or quiescent, and a particular phase of the interstellar medium, which is dust. Actually, dust covers many phases of the medium, but I will focus on how is dust in the central parts of galaxies. And to our surprise, or at least to me, I was found in this project. And actually this transparency is my conclusions. I will try to get there. I think I make it because it's not very long talk. And to my surprise, we found that dust is a systematic. We always see dust in the center of galaxies all the time. Even in galaxies, you might think there is no dust because they look very clean. Well, you go to the center, it's there. And because our angular resolution, we can resolve this dust in the center of galaxies. And then there is another systematic here. It resolves in filaments and lanes. And these filaments and lanes, as you will see now, we see that there are hundreds of parsecs or kiloparsecs distance. They go to the center. They flow to the center, you will see, and they cross the nucleus, and sometimes they obscure it, and sometimes they partially obscure it. And because some of the objects, many actually, are active, I will now make a parenthesis and say that these filaments might play the role of what we, one of the major pillars in Active Galactic Nuclei, which is the torus. And just to introduce you, for those that for sure you heard about this AGN torus, but we have two major fundamental classifications in active galaxies, those that are having the nucleus obscure. We do not see the broadline gas, and those that have the nucleus not obscure, and we see the broadline gas. And there is a structure that is very, very clever one introduced more than 20 years ago, that is this torus, a very tiny structure that we put at the center. It's usually dust, molecular gas, and with this structure we say, okay, all these objects, regardless if we see the broadline region or we don't, we see the nucleus or we don't, it's all the same, but it's just this torus that we put at the center that prevent, in some cases, to see the nucleus, to prevent us to see the nucleus. So I will make the case or the argument put forward that these filaments can play the role of the torus. Maybe we don't need this additional structure, but these filaments do it. They obscure sometimes, they don't obscure it. They can account for all the properties that torus is supposed to do. These are facts. I will try to show you how are these filaments, how are they doing. I will try to show you what I think is the role, because they are coming to the center, they come from kiloparsecs distances, and I think that the role of these filaments is to provide material to feed the star formation, to ignite the star formation, to produce a star formation, to activate a star formation in the center of galaxies, and to feed the hole as well, to feed the black hole, to make a reservoir of material that the black hole has at disposal to activate it whenever you want, whenever a material has loose moment. That is what I think is the role of these filaments, despite all the fact that they. So I wanted to start to show you how we get this dust, how we see these filaments, and I will illustrate it, how we produce a dust map. I will refer all the time about the dust maps that we produce. And to do that, I will take an example, one reference object in astronomy, definitely in the field of Active Galactic Nuclei, which is 1068. Sure you heard about, because it's a very bright source. It's a reference for a obscure nuclei. So we don't see the nucleus of this galaxy in the optical or in the UV. We don't see the borderline region directly as well. So this is 1068, the central kiloparsec region. This is an optical image you have on your left, and you have an adaptive optics image on in the red, in the infrared. They have comparable resolution, the same field of view in both images. And you might notice that the galaxy looks very different because in the optical it's completely covered by the dust, and it creates this patchy structure that we see. In the infrared, that is very kind infrared and allow us to see the galaxy through, and it looks very homogeneous, uniform. And so our dust maps are a very simple thing. It's simply divide the infrared by the optical one. When you do that, because the infrared is not subjected to dust, the ratio is something like this image, the same field of view again, and enhance those regions where the dust is located. Okay, these dust maps are not so simple. I just simply do a ratio. You have to have comparable resolution, because otherwise you create artifacts, and you have to do very good registration or astrometry between the two images. And the key here is never use the nucleus to align one image to another, but use other sources that you have in the field. That is the very important aspect. So when you do that, you get this dust map, and you might notice that now things where the dust is are brighter in color here. So where most of the dust is, or more the brighter emission you see here, is towards the center. You already see quite a filamentary or diffuse emission here. Since our goal is the very central region, let's make a zoom of the central to our second, just 100 parsecs, so 200 parsecs radius from the center. And you see all this diffuse emission. This is all dust, with regions where there is no dust, holes as well. The nucleus is here and is surrounded by this kind of bracelet or horn. Okay, this is a qualitative form. On the right side is the same image, but translated in optical depth, in extinction. Okay, so you have the bar here of extinction. The darker, the higher extinction, the higher depth, or thicker the dust. And of course, at the very center is very high. As I said, this is an obscure nucleus, quantum thick in addition, it's very obscure. And you have less thick, a little bit less thick in the surrounding, and less getting farther away, and regions where you see the dust. So towards the central region, you may read here that we have extinctions about 8 magnitudes, where 8 magnitudes is a lot, and of course is more than enough to skew the nucleus of these galaxies in the optical and in the UV. We can hide it completely. Okay, so okay, that is for 1068. This is a very particular object, very bright, but you see that we get a lot of extinction to obscure it. Let's see it with more normal obscure nuclei. What happened? So, and with having less dust in the galaxy. So this is another 2 galaxies that we study. Oh, me pasa. One that is a bit very much less luminous, much more quiescent than 1068 is this galaxy, and the image in color is the optical image. In contours is the infrared image. Below is something a little bit obscure nuclei as well, but a little bit brighter. This is 2 orders of magnitude in volumetric luminosity respect to the former, respect to the 1068. So it's very quiet. Here is 1 order of magnitude less than 1068 in the nucleus volumetric luminosity in power, if you want. And you might see already from these 2 comparison contours and optical images that both follow each other very nicely. The optical image is quite uniform. It's not like in the former case. Okay, so you will see, well, there is no much dust here, but it's not the case. You do this ratio, that's map, infrared by optical, and then you get all this structure here in the center, not around. And even here, you have a little bit of dust. You have a kind of very slim structure. I don't know, it looks like a disc or a filament if you want. Here we see a bit the nucleus, so that's why it appears here bright. And here on these panels is a zoom of the central few hundred parsecs that you see in detail how is this structure is filamentary and is spiral, looks spiral towards the center. Here again, kind of slim disc or maybe a filament in each bone, I don't know. And we translate in optical thickness. And you see now here a bit more in contrast the filaments and how they spiral towards the center. We have extinctions about 3 magnitudes. This is a very mild nucleus, so 3 magnitudes, 10 to the 42, or 2 order magnitude below the former case, 1068. Of course, it will obscure the nucleus of this galaxy in the UV and in the optical. In this one, which is we know is a partially obscure, we see a bit the nucleus, the extinction is only 1.5, so the object is brighter, therefore it's obscure, but not completely. In this object, we see a bit of the broad line gas, okay? It's consistent. Now, for type 2, somehow for obscure nuclei is what you will expect. By definition, we know that they are obscure. We don't see in the optical, we don't see in the UV, so normal we see all this dust. My surprise was that when we look at equivalent galaxies, similar distance, but which we know the nucleus is not obscure, like these ones, the same structure, we see exactly the same structure, so filamentary and a lot of dust, always at the center. So I here to show you the situation, I choose the upper panel is an image, very bright, an obscure nucleus. It's almost like a quasar, it's extremely powerful, comparable to the first case I showed you, density, even more powerful, I would say. And below is a very mild nucleus, sombrero gas, very mild. Okay, is doing sombrero has very low activity. And on the right is directly already just the dust map infrared divided by the optical. And you might already see this type of structure here. We are already in scales of, this is about kiloparsecs. And so you might see this kind of structure here, and sort of might see a spiral linking to the center or pointing toward the center. In sombrero, you see this kind of dust as well in a plane. It's not the dust lane of sombrero. The dust lane is here down. Okay, the nucleus of sombrero is above the known dust lane of big dust lane of this galaxy. Both galaxies you see in the UV, the sombrero as well. And let's make a bit zoom and central few tens of parsec, and then you see a bit much better this filament here, another one here, getting towards the center. The nucleus is very difficult to see what happened because it's so bright, they basically blind us. We cannot access directly, but I think you get an idea of this type of filamentary structure already in this galaxy that we see completely. And also in sombrero. Okay, we see the nucleus in sombrero. There is a lot of dust as you see around crossing it. Okay, what happened here? Let's see the optical depth. And well, the optical depth, what happened is that it's very low. That is why we see the nucleus. We see all these filaments, and now with much more better contrast, but it's only here 1.5 magnitudes. It's such a powerful object quasar, you hide it. And in sombrero, it does almost not get to 1 magnitude, a bit more. It does very little also because the filaments, when they get towards the center in sombrero, are very mild, they don't do much. So we see the nucleus. Okay. So all is this about what is the morphology of these filaments. Let me tell you a little bit about the origin and the structure. You see that there are the image I showed you before the war, in some cases standing the structures up to kiloparsec region, or 100 parsecs, let's say, I can follow them towards kiloparsecs or even sometimes outside the galaxy as a coherent structure. And I want to take as an example this galaxy, is very well known. This galaxy you see here, you have these grand design spiral arms around, and these spiral arms end up at the edges of the disk of the galaxy in this dust lane, one here, one less obvious here. The nucleus of the galaxy is at the center, is bright. It's a very mild nucleus in terms of activity, very low activity nuclei. And actually, this galaxy is well known because of what it has here, this ring, which is very bright. It's a ring of star-forming rings. Hundreds of star clusters are there. We have studied this in detail, by the way, very nice. But it's not the point. I'm not going to focus on that. It's just to show you that the dust lane gets from the disk of the galaxy. You already see it's quite structured, filamentary as well. You might see the gets towards the ring, cross it, and well, we don't see, we can guess what happened. Let's zoom this area of the lane towards the center as well, what happened here. Angular resolution is what we are playing here. It's a space telescope image, there's no ratio here. This is a direct image, okay, nothing else. So you see what the lane is producing, it's skewing a lot. And the galaxy, you see, is quite structured. Really, you might notice here, there are like filaments, 1, 2, 3. They get to the ring, they cross it. It gets inside, you might see already kind of filamentary here. Actually, it gets into the center, circularized around the ring and towards the nucleus. Let's zoom a little bit more, better angular resolution, but it's a ratio. Now we are with a real dust map. Okay, we are emphasizing where the dust, again, dust map is. Here is the lane as well. You see all the structure crossing the nucleus. Some of the filaments, the structure goes along the ring. Some other, you might already notice they circularize from different regions as well. Okay, but from this region in particular, they circularize. The nucleus is here. This nucleus is visible. Okay, up to the UV. There is a lot of dust, but we see this nucleus because the filaments are not having very much optical depth. And if we get a very sharp image with AO from the center, we get this. Now we see in very much detail, the best we can do, all these filaments, very sharp, getting in spiral towards the center. You can continue here. You see this one here, that goes here, 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 up there, and other ones, and from other regions as well. Okay, from other regions, you follow this filament all showing a morphology of a spiral to the center. How is the structure? Actually, this is many filaments. What we call here is kind of a streamer with combination of sum up of many filaments all together running through or through the lane, if you want. So let's make a cut or one of this in this region. That you see already like 2 fingers here, more or less here. Let's make a cut to see the structure. Simply a cut around the image, and then you see how this lane or that lane is a structure. Many different peaks. We can count here about 400 parsecs width, and one of each of them is a filament or maybe a bundle of them. I don't have enough resolution. Actually, the width that we measure for each of these peaks is about 20 parsecs, but 20 parsecs means a little bit, well, it does not mean much because this number is limited by the angular resolution we have there. So it must be much smaller than that. We can get an idea of the filling factor because we can count the filaments there. We see them separately. And also the column density, because this is a gas map, so we can see how deep is the density. The volume density is not very high, so okay, it's they obscure the galaxy, but it's quite mild, and there are quite a lot of spacing between the filaments when there is no obscuration. Okay, so that is how I made it for this particular case. Most of the filaments that we are seeing in other galaxies is this type, this thing. But here I wanted to illustrate it because we can trace it from kiloparsecs distance all the way to the center. That is what I want to say. Not always is the case, but in some cases we see that. And actually, this is not very different to what we see in our own Milky Way. It's not, in a way, I'm not saying nothing special or particular. The Milky Way have the same type of structures. Okay? Now that is the resolution we have, we can compare and realize that well, it's similar. So this is the center of the Milky Way. Okay, here we have our Sagittarius A star. This is the central 100 parsecs or so. This is a direct image in dust. This is not a dust map. This is direct dust in emissions. Okay, this infrared, mid-infrared from satellites. Of course, when you go with satellites in the infrared for a galaxy like ours, we are very close. We can see a lot of detail, and you see all this kind of dust, filamentary structure in much more detail, of course, that we see when we go to galaxies, when we go to the extragalactic. And just to illustrate a little bit the comparison, this is one of the galaxies we studied with the nucleus of the galaxies here. It's also the 100 parsec, the central 100 parsecs. You see again this filamentary structure, and the way the reason why I choose this galaxy, which is this type of early type galaxy here, is because it shows like kind of loop here. Well, it happens that in Sagittarius A in the center we have a kind of loop here, similar. Accidental, I don't want to make any point. It's just to illustrate a little bit that in global scale, we see this type of structures developing in the central 100 parsecs of galaxies, exactly like in the Milky Way, or even in Andromeda, which is another sample. Here, this is the central 100 parsecs of Andromeda. The nucleus is here. Andromeda, the nucleus is visible. We see it to the UV. There is a lot of dust in Andromeda. And in the center, there are, again, this type of very fine, very well-defined profile structure. You might even see that spiral towards the center. This is not a dust map, again, also in Andromeda. This is a direct dust image. All what you see here is dust all around here. And you see this kind of curvature of carving, of circularizing, hint, if you want, for circularizing with the center here. Okay, so far is what I try to show you a bit with the type of morphology in a qualitative manner, where sometimes these filaments might arise from large distance, not from the center, from larger distance. I didn't say much about the nature, so it's my next question. What is the nature of these filaments? We only see the prints, obscure prints in the galaxy. We don't know much about what are they. And of course, the immediate think of one of the ways to search for it is in molecular gas. That's personally we see in molecular gas. So this is an example, 3 cases. 1068 again, I showed you before, this does map here. And this is the case I showed you before with the very profile spiral structure toward the center, 1097. This is another galaxy also showing this kind of spiral structure, but it's a network of filaments which is much more dense than here. Here you see very well separated. There are no, this distance is very similar in between, in all of them in addition. But here is more separated, here is more condensed. This is a more active nucleus. This is very mild, nothing. This is a quite active nucleus. Here is no obscure. Here is, here is obscure, and here is no obscure. So here you see the nucleus very nicely. And below, again, you see the counterpart in molecular gas, and we see in different traces. Not always we see all the filaments in tracing molecular gas, but quite a number of them we can trace it very precisely. So for 1068, we see this is the map in molecular gas, warm molecular gas, in 2 microns, symphony data. That, it traces nicely this molecular ring that we see here, we trace in molecular gas. And you might notice here a kind of hint or tongue that gets toward the nucleus, which gets somehow between these 2 horns. You might notice as well that, for example, this structure I make a point before, we do not see, I have not seen it so far, a counterpart of this dust region, this bracelet in molecular gas. In H2, we look at it, and in CO, we do not see it. We see the circumnuclear disk in CO as well, but not precisely this structure. This kind of tongue is seen as well in CO too, depending on the transition in CO, but you see it. And we can go to the next object, this one, and again, you see contours. It's difficult to show the comparison that you can have an impression altogether, but you may say that here is the nucleus and kind of spiral structure getting towards the center, like we see here, or this arm here, a bit of this one. There are structures we don't see in molecular gas here. So it's not necessarily the same phase of the medium might be reflecting a particular transition in a particular component of the medium. Is my interpretation that we can set. And you have this other galaxy too that we see as well, very well imprinted in molecular gas and CO as well. So we see it's not easy to get this counterpart, because you also need very high angular resolution in the molecular gas and get toward the center, and the structure could get a little bit complex. So if there is, the system is very complex, it's difficult to disentangle structures and compare. No obvious, but a few cases it has been possible to do that. So, and of course, if we have molecular gas, the next question immediately is what are the velocities, what this is doing, what the gas is doing. And it happened in all cases. We have a few more than here. The gas is in addition inflow, okay? When you trace the filament and you trace it in molecular gas, you can trace the velocities, and it happened that this gas is moving in. And to be honest, to interpret these kinematic maps for these structures and very close to the center is not trivial, it's not obvious. So I just illustrated by different people how they do. This is a work for Muller, Sanchez, and you see here the kinematics of the H2 gas, the one I showed you before, this one in contours, exactly. So you see that they have positive and very high velocities, positive and negative in the central region. This region is about 100 parsecs. The nucleus is here, and what they do is they see this kind of tongue. I showed you, I tried to illustrate it or point it out before. That gets among this horn here. If I go this type here. So is this one, now this is a very high angular resolution map in H2 again, the velocity. And so what they do is they try to fit elliptical orbits that match with the morphology that we see of the filament and with the velocities. And so with that, they can infer what the gas is doing, because directly it's quite complex. At least we can say it's not rotating, but the kinematics is difficult to interpret. Here is in this other galaxy, what the people do is not from the CO map that I showed you before that shows the counterpart, but is from HCN, where the evidence for inflowing is determined, and this is the kinematic map, quite complex, but it's after subtracting the rotational component. So you see the residuals here. So you see this is it's not a very direct way of doing. Residuals always have uncertainty, but okay, they claim that there is kind of enhancement in certain directions, which goes with this arc, this spiral. It's not a spiral structure that we see in the curvatures of the filaments, spiraling. And from that, they interpret the gas is inflowing and the velocities. And here we have in this other galaxy, this is the direct kinematic map, just to show you how it looks like. And of course, from here, you might notice that it's not from Francois Combes, this is from Fatih, and the kinematics is quite complex, positive, negative velocities towards the center. So it's not trivial thing to do. So having these velocities, identifying the filaments that are associated with the velocities, doing different treatments of the velocity field, and we can infer, of course, inflow rates, because we have all the information. We have an idea of the velocity, we have an idea of the filling factor of these filaments, as I showed you at the beginning. We have the morphology, so we can infer volume densities as well, because we have the column densities from the dust map. So we have basically all the ingredients to get a reasonable estimate of the inflow rate. We have valid information, or we have to guess a lot about projection effects. This is a major problem. Also interpreting the kinematics in inferring the velocities. So this is, we had to deal with it. Yes, we wanted to tell you all the shortcuts. It's not all positive, and identifying the filaments we are done. No, it's quite a lot of uncertainty as well. But I would say that even all that, numbers that come out are comparable among each other in a way, in order of magnitude, if you want. So from 1068, these people, they infer inflow rates of the order of a few solar masses per year, at distance of 10 parsecs. And also from Tacconi, I don't know why it appeared the reference, Tacconi also, Linda Tacconi, Tacconi as well. Here in this case, the inflow rates that are inferred are, well, between 3 and half of solar mass per year. depending on distances. So as we get closer to the center, the inflow rates are smaller, which is somehow good, at least, because this means that we are losing momentum. This is the way to approach the center. And in this case, we had to do a little bit careful estimate of the inflow rate, but we could identify a filament, which is this one, which gas a perfect counterpart in molecular gas. Actually, filament is below, you don't see it, because it's covered by the filament, the molecular gas. So we identify not only a filament morphologically comparable, but kinematic component is also coherent all along the filament. So we could trace along the center and derive these numbers, 0.2. So you see, half a fraction of solar mass, several solar masses per year. That is the range, depending in scales of 10 of parsecs. What does it mean, these numbers a priori? Well, are not very different among them, just to start with, but could be any number perhaps. So we cannot do much than this. Instead that, of course, it seems that the material is inflowing towards the center, and if it's inflowing, might get towards the center, it has to lose momentum. That's clear. And at least we can say that these numbers we are getting different authors from different galaxies are order of magnitude superior the accretion rate, what you will measure or what you will estimate, because we don't measure accretion rate, unfortunately. But taking into account the black hole mass and the luminosity. So this is accretion rate. I put it for few objects well, the objects I just showed you before. And so in 1068 is at least 3 order of magnitude above. In this object, about 1, about 2. Andromeda is very quiescent one. We are doing this analysis much more complex for inferring inflow rate, because we have to do hydro simulations of the filaments and so on. So it's 10 to minus 7, because this galaxy Andromeda nucleus is doing nothing, but we get to order of magnitude superior. So what does it mean? It means that at least as a minimum, we have enough material to get to the center, in principle, to get a reservoir and account for this accretion rate that are very small. We need very little to need an AGN, but we are enough, and we are still at several tens of parsecs. We had to get to a Schwarzschild radius to lose momentum. So overall, in a very fast order, we are about okay. It's not something weird or wrong or difficult, and we are losing momentum as well. We see the inflow rate change. So here I end up, and that is getting to the end. I tried to show you some facts about the presence ubiquitous of dust in the center. That is very collimated. It's very coherent structure over long distances. That you get this filament all the time to the center, and at the center you see two forms, basically, either they spiral to the center or simply cross it. And depending on the optical thickness of these filaments and the luminosity of the nucleus, these filaments can obscure the nucleus or partially obscure it, okay? That's it. Or whether they fall next to the nucleus or not. And by tracing them in molecular gas, we see they are inflowing and losing momentum. So that's like a fact. So the way I read the images, and you have them, I showed you them that you can judge by yourself whether this is about correct, but it's what I read it. I don't interpret it much, that read what I see. If these filaments are inflowing and losing momentum, and these morphologies and spiraling is also a hint for losing momentum, I will interpret them as having a role, not just being there and doing all that, but having a role. And I think that the role, or why nature put them, is that they are really very important suppliers of material to feed the center, to feed the hole, to accumulate in the reservoir, in the accretion disk. They have to lose momentum, as I say, But also, although I did not say, these filaments get to the star-forming region, they might emit, because you supply material, they might emit and activate the star formation center. And the second aspect that I mentioned at the beginning is that these filaments, in the context of active galactic nuclei, are, I think they are very good alternative to the torus. That this filament, the difference, the filaments are very long structures. These are no parsec-scale structure like the torus with a certain morphology or inclination or position respect to our line of sight. These are filaments that are there, and well, they cross the center and sometimes obscure, sometimes not, produce or account for many of the properties, or most of them that come with the torus. And that's it.
Thank you very much, Almudena. Do we have any question for Almudena? So please raise your hand in the chat interface. I can see some applauses also here. Let me see. Thumbs up from some other people. I have one question, Almudena, and it's so can you explain us a bit what will be your idea about how can you quantify all the different scenarios based on this data? How can you move on from the morphologies, for example, or the contrast between the arm and inter-arm region, and something quantitative? So you think there is an easy way to handle that kind of problem? In general, I mean, I'm talking about in general terms.
I'm not sure to, I mean, I'm not sure to understand if I can quantify why they are sometimes spiral. I think there is nothing particular about this filament that are structures that we have in the galaxy. But I'm not sure if I get precisely.
No, if you want to compare, for example, the morphology from one galaxy to another.
Okay, between galaxies. Well, that was the point, that regardless of activity level, in the nucleus of the galaxy, we have a galaxy like Andromeda, which is doing nothing, or a very active nucleus like a 1068, which is really exploding. We have these filaments there. So in all cases, there is supply of material, but the supply of material does not mean they activate the nucleus, because you simply, with this material, you feed a reservoir, and then it's a disposal of the black hole to activate it or not. Okay, so in Andromeda, we are seeing these filaments arriving to the center. Actually, we cannot connect directly to the center. That is the nice thing here. So probably it's because that is why Andromeda is very quiet. In other cases, we see the nucleus is very mild, but the filaments are there and the flowing material is there. Well, obviously, we are getting this material eventually might get in the Schwarzschild radius, is getting in the accretion disk, but if they does not lose momentum, it won't activate the nucleus. So that is the next question, how this material further lose the momentum to activate the nucleus. But what we get up to now is a way of feeding this accretion disk. And regarding star formation, in some cases, we are seeing the star formation. No conditions for star formation, no is always to have material start, but we are these filaments provide the material to start with as a minimum. So it's a little bit away perhaps of these scenarios which are now more on the feedback and the black hole is active and expel materials towards the galaxy, and this expelling might quench star formation, and then the winds of the stars might feedback or get material towards the nucleus. Is a little bit more close scenario where everything happens between the center, the nucleus, the black hole, and the region around. This is a much more larger scale, like the galaxy knows or have a duty to provide material and be like a vacuum cleaner, getting things along the galaxy and moving towards the center. Does not mean always that is the final effect is activate the nucleus. We had to pass by the problem of angular momentum.
Okay, thank you. We have a question from Luke Binet. Luke, please go ahead.
Hi, good afternoon, Almudena.
Hello, Luke. Nice to see you.
Yes. I have a question. Well, I missed a part of it because the computer just blocked. I don't know what happened. So there's about 2 orders of magnitude more accreting rate, well, no, accumulation rate to the nucleus than there is actually accreting the black hole, more or less, right?
Mm.
And I missed, maybe you mentioned it, but what happened to this material that accumulate there? Where does it accumulate? If it doesn't go to the black hole, does it get expelled as from the HCN due to the accretion mechanism around the accretion disk, or what?
It could be that it's a spell, in particular in those that are active, but I think that the major thing is that we have the accretion disk. Our accretion disk is our reservoir. So if the accretion disk does not have, if we don't have the right mechanism for this material to lose momentum, I guess that this material might get to the accretion disk and it will be rotated forever until it loses momentum. So we need something. What is this mechanism, or what is this phenomenon for having this losing angular momentum is a question. But if it all gets there, and there is no, as you say, a black hole is active, by being active might expel out material. If it does, might simply evaporate it as well. But if it's doing nothing, this gets in, and well, you eventually might lose angular momentum to get to the right values at the Schwarzschild radius to get into the center, or you simply accumulate there and rotate.
It could form stars, presumably, as well.
As well.
And then they don't need to lose momentum anymore.
Yeah, exactly. Yes.
Okay, thank you. Very impacting images you've shown.
Okay, thank you, Luke. Any other question for Almudena? Let me have a look at the... Okay, if you don't find how to raise your hand, you can also speak up, no problem. Okay, so if there are no more questions, let's thank Almudena again.
Thank you.
Thank you very much, Almudena, and thanks a lot for your talk, and thank you everyone also for joining us. On Friday, we'll have a talk in morning time at 10 a.m. European summer time by Roser Pelló. So I encourage you to attend also. So thank you again, everyone, for participating in the IPARCOS seminars. And hopefully I see you on Friday.
Okay, thank you.
Bye-bye.
Ciao. Ciao.
Bye-bye.
Thank you, everyone.
Ciao.
Bye.